Hello everyone. Waves 2. Displacement relation in a progressive wave and the speed of a traveling wave. These are the two topics that will be discussed in this video. So first we shall see the displacement relation in the case of a progressive wave. This animation shows a progressive wave. For example, we can consider a string which is attached to a wall at one end and the other end of the string is moved up and down by a person to create waves as shown in this figure. In this case, the particles vibrate in the y direction and the wave propagates along the positive x direction. The displacement relation for such a wave is given by y of x of t is equal to a sine kx minus omega t plus phi. In this case, yx of t is the displacement, a is the amplitude, then kx minus omega t plus phi is known as the phase, in which k is known as the angular wave number, omega is known as the angular frequency, and phi is the initial phase angle. Now we shall see all these concepts in detail. First is the amplitude and phase of the wave. The amplitude of the wave is the magnitude of the maximum displacement of the elements from their equilibrium positions as the wave passes through them. Amplitude is always a positive quantity since it is a magnitude even if displacement is negative. The phase of the wave is the argument kx minus omega t plus phi of the oscillatory term sine of kx minus omega t plus phi. It describes the state of motion as the wave sweeps through the string element at a particular position x. For example, if the wave propagates in the negative x direction, then the equation becomes kx plus omega t plus phi. It changes linearly with time t. The sine function also changes with time, oscillating between +1 and -1. And based on this, the maximum and minimum amplitude of the wave are observed. The constant phi is called the initial phase angle. The value of phi is determined by the initial, that is when time is equal to 0 displacement, and velocity of the element. Now wavelength and angular wave number. The wavelength lambda of a wave is the distance which is taken parallel to the direction of wave propagation between the consecutive repetitions of the shape of the wave. Or we can say that it is the minimum distance between two consecutive troughs or crests or two consecutive points in the same phase of wave motion. Angular wave number describes the number of wavelengths per unit distance. It is denoted by k, which is also called propagation constant because it tells about the propagation of wave. And the formula for wave number is equal to 2 pi n by lambda, where the value of n may be any natural number starting from 1. Period, angular frequency, and frequency of a wave. The period of oscillation T of a wave is defined as the time any string element takes to move through one complete oscillation. Angular frequency is defined as the frequency of the wave in terms of a circular motion. The term angular frequency is used only when there is an angle involved in the motion, in that particular motion. It is denoted by omega. Now frequency nu is the number of oscillations per unit time made by a string element as the wave passes through it. It is usually measured in hertz. Now the relation between period angular frequency and frequency is frequency nu is equal to reciprocal of period is equal to omega by 2 pi. Here omega is the angular frequency, t is the time period and nu is the frequency. Now we shall see how to calculate the speed of a wave. In this figure, we can see two positions of the wave propagating along the positive x direction. Let us observe the position of point A. Let us consider the position of the wave after a small time interval delta t. In this case, the displacement is given by delta x. Now since at both the positions the phase of the wave remains the same, we can say that kx minus omega t is equal to constant. Now differentiating on both sides, we get k into dx by dt minus omega is equal to 0. Or dx by dt is equal to omega by k. Omega, which is the angular frequency, is given by 2 pi by t. And k, the wave number, is given by 2 pi by lambda. And 1 by t is equal to nu, or the frequency. Hence, we get the expression for velocity of a traveling wave as velocity v is equal to nu into lambda, or it is the product of frequency and wavelength of the wave. Now we shall see the speed of transverse wave on stretched string. In this case, the speed depends on the linear mass density or mass per unit length mu and the tension T. This is because the mass is required so that there is kinetic energy, and without tension no disturbance can be propagated in the string. Now we shall derive an equation for the velocity using dimensional analysis. For that, we can first consider the dimensions for mass per unit length mu, which is ml raised to minus 1. Now the dimension for tension or force is equal to ml t raised to minus 2. Now mu by t is equal to L raised to minus 2 t square is equal to t by L square is equal to 1 by v square, where v is the velocity of the wave. Hence we get the expression velocity of the wave v is equal to c into root of t by mu. Here c is a dimensionless constant. Now the speed of the longitudinal wave of sound can also be found out similarly. The speed of longitudinal wave depends on the density and the bulk modulus. Bulk modulus tells how does the volume of a medium changes when the pressure on it changes. Now rho, which is density, is equal to mass by volume, and the dimension is equal to ml raised to minus 3. Now the dimension for bulk modulus is equal to minus of change in pressure by change in volume. Here change in volume, since it is delta V by V, is dimensionless. Now we shall see the dimension for pressure. Delta P is equal to force by area. And hence we get the dimension for pressure as ml raised to minus 1 T raised to minus 2. Now if we divide rho by B, we get rho by B is equal to 1 by V square. which is the dimension for velocity. Hence from this we can say that v, which is the velocity of the longitudinal wave, is equal to c into root of b by rho, where c is a dimensionless constant. This is the case for fluids. In the case of solids, the bulk modulus is replaced by Young's modulus y. So this is the end of this video. In this video, I have discussed the characteristics of a wave. If you have got any doubt in any of these characteristics of the wave, please comment in this section below. Thank you.